So we are back live. Welcome to the second part of today's lecture, where we are going to work with grammars and languages once more. So before we look at, well, actually, let's look at the example that we have there, and let's use the example to introduce the last two bits of formal notation. Now, let me give you intuitively once more the notion of a language generated by a grammar. The language generated by a grammar consists of all the strings of terminals. T star is the collection of all strings that you can write using the characters in T, and these are the terminals, that you can derive from the start symbol S by applying rules. That's what this arrow star means. Arrow star formally is the reflexive transitive closure of the arrow of the rewriting, of the one-step rewriting relation. Have you met this notion, reflexive transitive closure in discrete math 1? You haven't. That's not so good. But anyway, it's very simple to explain. You've looked at graphs, isn't it, in discrete math 1? I hope the answer is yes. I know the answer is yes. Graphs. Stærðfræði. Collection of nodes and edges. Okay? So one of the key questions is reachability. Can I go from one node to another one by following edges? And if I do that, I do it by following a path of length 0. Well, if I want to go to Reykjavik, it's easy, I'm already there. So it's a path of length 0. That's a reflexive part. I can go from where I am to where I am. Transitive means you can follow any number of paths. So I can go from Reykjavik to Rome by first flying to Milan if it's summer, and then flying from Milan to Rome. That's 2 steps, but they form a path. That's what reflexive transitive closure is. It's following a path of rewriting. So since this is the language generated by a grammar, if I ask you, what is the language generated by the grammar that you have on the slide? What would your answer be? So if you were to describe to me in plain English, okay, one of your colleagues right at the back says all palindromes of even length, and that's absolutely right. Now, in order to understand this answer, we need first of all to know what a palindrome is. I know he does know what it is, but what is a palindrome? It's a word that's the same forwards and back of the string. Absolutely. A palindrome is a string that reads the same from left to right or from right to left. Or in other words, it's a string that is the same as its reverse. Now, these are not all palindromes, but are the palindromes of even length. Namely, the length of the palindrome is an even number. Okay, so let's convince ourselves that this is indeed the case. We take out our scratch pad, digital one. You take out at home your scratch pads, physical ones perhaps, unless you have a writing tablet. Let me rewrite the grammar. And let's assume, for instance, that I want to derive the palindrome 0, 0, 0, 0. Or let me make it slightly more exciting. I want to derive the palindrome. Oof, I don't like this. Let's do the handwriting and let's do it black just, okay? So 0, 1, 1, 0. That's a palindrome. If this grammar is a grammar that allows us to derive all palindromes of even length, this one is of length 4, so it's of even length, we should be able to derive it from the start symbol. So how do we do it? We start from S, and we start applying productions. Which production should I use first? The second one. You rewrite S to 0 as 0. In so doing, I've written the first and the last symbol in my string. So what is left now is to write the 1, 1 to derive the 1, 1 in the middle. Okay, so what production should I use next? The third one. It's the only one that allows us to write a 1 at the beginning and before and after the S. So what I do now is I just replace the S, which is in the middle, sandwiched between the two zeros, by the right-hand side of a production for it. So I just leave the 0 untouched. I'm not doing anything to it. I'd already derived it. I replace the S with 1, S, 1. And then I write the 0 that I had after the original S. So this has been changed to that. That's the application of the third production. Okay, what next? Now I want to erase the S. How do I do it? By using the first production that says you can replace S with lambda, the empty string, which means instead of S, write nothing. This corresponds to erasing S. Bingo, we are done. In fact, we can derive any palindrome of even length in this way. We just use the productions that allow us to write zeros at the beginning and at the end, and ones at the beginning and the end as appropriate, and then we remove the S that we have in the middle. That's exactly the pattern that we have used now. The only thing that changes is how we apply the pattern, depending on the string that we want to derive. Now, suppose that I'm interested in generating in having a grammar that generates any palindrome, not just those of even length. You can also have palindromes of odd length. For instance, a single digit, 0, is a palindrome of length 1. It reads the same right to left and left to right. So what do you think I should add to this grammar in order to generate all palindromes? Your colleagues are saying here, well, we need more base cases in our recursive definition to account for the fact that 1 is a palindrome and 0 is a palindrome. Why does this work? Well, you want to generate a palindrome. Okay, if it's a base case, so a palindrome of length 0 or length 1, then you use one of the productions that immediately generate it. You either write S to the empty string, S to 0, or S to 1. But if it's a longer palindrome, then what we know is that the palindrome will start and end with the same symbol. So it will start, say, with 0, end with 0, and in the middle, there is some string W, which is what? What is the property of W? So if 0W0 is supposed to be a palindrome, then W is what? 1 or 0, but it's a string. It could have perhaps 1 billion zeros or 1 billion and 1 zeros. Is it a palindrome itself? Sure, it must read the same from left to right and right to left. Otherwise, our original string is not a palindrome. Okay, so that's where we have the recursion. That's where we have the recursion. Since it's a shorter palindrome, we can derive it from S. So this can be derived in 0 or more steps from S. Which means that if we want to derive a string like that, all we need to do is to start by writing S goes to 0 as 0, and then we do the amount of work that it takes for us in 0 or more steps, in fact 1 or more steps, to derive W from S. And we are done. That's the recursive reason why this grammar actually works. It works for the base cases, and assuming that it derives a string W, it can derive any longer palindrome with just W in the middle, preceded and followed by 0 or preceded and followed by 1. That's why it works. Without announcing it, we've done an inductive proof of the correctness of this grammar. It's better to discover it later, otherwise if I tell you, let's do an inductive proof, then you get scared. Or some of you perhaps get scared. There is no reason to. Induction is your friend, like recursion. Any problem with what we have done? Do we understand how to generate a string using productions from the start symbol? That's really the goal of the game. In fact, you can do it at home with your boyfriends, girlfriends, husbands, wives, whatever you like, children. They will like this game, perhaps. It may work if you want to get rid of them as well, but that's another matter. At least in that case, you get a few moments of peace. Yes? Okay, the question is, how do you define this language LG in the example that I gave? Okay, so this is essentially the example that we were looking at. Now, this is the grammar G. L of G is the collection of all bit strings which are palindromes. You can write it in English. Yeah. So basically what this says, L of G is the collection of all the strings of terminals, that's what this T star means, that you can generate by applying productions 1 or more times in a row from the start symbol. The single arrow stands for one rewriting. I use one rule once. The star on it means you can do it any amount of time. Any finite number of rewritings will do. And this finite number could be 0 rewritings, but in that case, if you start from S, you get S. So it will not generate a string of terminals. Excellent. Now, what we've done so far is to say, okay, here's a grammar, let's see what it generates. But grammars are there because they're supposed to generate languages. Very often, what we have is a language, and we ask ourselves, what grammar can we come up with to generate that language? So if you will give in a grammar as programming, which is really what it is, this is really the task of programming after a specification. Somebody gives you, your programming language are grammars, and I'm not joking, they are programming languages, just full-blown programming languages like C++, only more powerful, in a very strong sense. Somebody gives you a task. Here's a language I want to describe. How can you actually generate a grammar, that is to say, write a program in the formalism of grammars that generates exactly the language that that person asked you to generate? Now, that person might say, okay, if you don't get it right, I'll chop one of your fingers or do something nasty to you, so you better get it right. How do you do it? Well, remember, grammars are recursive objects. So a way of getting it right, and the best way of getting it right, is to think recursively. Ask yourself, what are the most basic strings in the language that this person asked me to give a grammar for? Second, this will be the base case in your grammar, the basic productions. Second, ask yourself, like in every recursive exercise, suppose somebody gives me a string in the language I need to generate. How can I make it longer and still get the string that is in the language? This will give you the recursive definition of the language that you want to generate. And once you have the recursive definitions, it's piece of cake to turn it into a grammar. This sounds abstract, I know. So let's put it to work. Suppose somebody tells you, give me a grammar that generates this language. Now, this language is a set of strings. What are these strings? In order to understand it, we need to be able to read what is written here. These are all the bit strings of a given form. Okay, so these bit strings start with a sequence of zeros. So this 0 to the n means you write n zeros for any value of n that you may care about, including 0 zeros. That's the empty string. And then what follows is a string of n ones. So for instance, the empty string would be in there. Why? Because it's 0 zeros followed by 0 ones. The string 0 1 would be in there. Why? You write 1 0 followed by 1 1. 2 zeros followed by 2 ones. 3 zeros followed by 3 ones. And now you see the pattern, I think. Even I have seen the pattern, which means you saw it long before me. So it's you're not allowed to intermingle zeros and ones, and you have to start with zeros. And the number of zeros that you write has to be equal to the number of ones that follow the number of zeros. Why don't you give a grammar for me and, well, actually, the people at home should do it themselves. So you only do it for me and for the colleagues who are in this room. Give me a grammar to generate this language. So let's put our scratch pad on. First of all, let's give a recursive definition of this set. What is this set? Okay. One of your colleagues is saying, I want to have a production like this. I want to put, recursively, I want to put a 0 at the front and a 1 at the end. Now, by itself, that's not enough. Why? Because if we only have this thing, there is no base case. We keep looping. We can never get rid of the S, the capital S. It keeps reappearing over and over again. It's like in a video game, you kill the bad guy and he keeps coming back. Resurrection. Forever. Okay, so we want a base case. Now, what is the base case? The base case should correspond to perhaps the shortest string which is in the language. The empty string is there because you get it by writing 0 zeros followed by 0 ones. Do we need anything else? Okay, one of your colleagues is saying, how about a production? Let me put it in a different color. How about a production that says, from S, you can write 0, 1. It certainly doesn't harm to have it because it's a good string. It belongs to the language that we want to generate. But is it necessary? No, absolutely, it's not necessary. Why? We can implement the effect of this production by means of the ones that we already have. So let's do it, and let's do it in red. You want to generate 0, 1. First, you generate 0 S1, and then you get rid of the S in the middle by rewriting it to the empty string. So it's not necessary, but good suggestion. Since we want to be efficient, we want to write as little as possible. Well, in this case, efficient is another way to say lazy, but there you are. Now, why does this grammar work? Well, I don't think I need to explain it, but let me explain it for myself. So suppose that I want to generate a string that contains, say, 35 where then you replace 35 by whatever number you like. 35 zeros followed by 35 ones. Huh? How do I get it? Well, I first apply 35 times the first production. If I apply the first production 35 times, and this is what the 35 on the arrow means, I get the string 35 zeros, then an S in the middle, and then 35 ones. Every time I add the production, I add the 0 at the end and a 1 at, 0 at the beginning and a 1 at the end. And now I just erase the S by using the second production, and I get 35 zeros followed by 35 ones. And of course, this process has nothing to do with the number 35. You can write any number of zeros that way, and any number of ones afterwards. The crucial thing is that every time you write a 0 at the front, you write a 1 at the end. This is how you keep track of the number of zeros and the ones that you have generated. Do you want to generate another grammar for me? I sense a lot of enthusiasm for this activity. Okay. So your colleague is saying, well, the language specification said n should be greater or equal to 0. What does this mean? This means that you get one string in the language when n is 0. That's the empty string. You write 0 zeros followed by 0 ones. N could be 1. So you write 1 0 followed by 1 1. You get 0 1. N could be 2. 0 0 1 1. N could be 35. 0 0 0 35 times. 1 1 1 1 35 times. N could be 3,344,000,000. You write 3,344,000,000 zeros followed by 3,334,000,000 ones. And how do you generate the humongously long string? By applying the production S goes to 0, S1, whatever number I said, a large number, and then I erase the S in the middle. All of these strings are produced in exactly the same way. What changes is the amount of work you need to do. The longer the string, the more rewriting you need to do. Just out of curiosity, have you seen set specifications like this before? I guess so, yeah. Okay, so let's do another example. This was not on my plans, but I'm flexible, I hope. Okay, so suppose I want to generate the collection of all the binary strings that end with a 0. So the language I want to generate is all the binary strings that end with a 0. So how are we going to do it? Okay, so that's the language I want to generate. These are all the strings of the form W followed by 0, where W is a bit string. Let's do tall pen, even though it's boring. Okay? So I suggest that we use a divide and conquer approach here. Divide et impera. Let's first give a grammar that generates all the bit strings. And then out of it, we build a grammar that generates all the bit strings that have a 0 at the end. So let me write the symbol A. Wow. Fantastic. This is a funky A. Let me write the symbol A for all bit strings. Okay, so what is the shortest bit string of them all? The empty string, of course. So let's start from there. Wow, what am I doing? Oh, this is a nice dotted line. Fantastic. Beautiful. Then at home, you fill the dots. Okay? So that's the base case of the recursive definition. Now you want to generate productions that implement the recursive construction of longer bit strings. Suppose somebody gives you a bit string that you can generate from capital A. How can you make it longer? So suppose I give you 001. Make it a little bit longer. What do? You add something at the front, isn't it? And this something could be a bit. So the capital A stands for give me a bit string. The 0 at the front says I'll add the 0 in front of it. This says give me a bit string generated by capital A. I'll stick a 1 in front of it. Note, this is exactly the same definition that we use for binary lists. It's just the syntax that is different. The process is the same. Okay, this generates every binary string under the sky, including the empty one. Now, what we want to say is, okay, I want only those that end with a 0. So let's add a start variable here. Now this should generate only bit strings that start with a 0. And what do these bit strings look like? They start with an arbitrary bit string, and then we stick a 0 at the end. So who can generate arbitrary bit strings? Who are you going to call? The Ghostbusters, or? We call A. We say, hey, give me an arbitrary bit string. Once you've given me a bit string, I stick a 0 at the end. And I'm done. Yeah, you are done. The general message is think recursively. It's again the same message that I've been trying to hammer for nearly 3 course sessions now. If you think recursively, you get it right. Keep it simple. The KISS method. Keep it simple, Sigurdur. Or whatever S name you like. Fantastic. Okay, so let me skip this more challenging example right now. We'll do it like some other time. Because I wanted to introduce to you a guy. Some of you might have heard of him. He's Avram Noam Chomsky, who's perhaps today best known as a political activist of sorts. But for us computer scientists, he's one of the fathers of the theory of formal languages. Oh, yeah. The question is, will I be tested about, or we will be tested about the man? Absolutely. I will ask you, how old is he on this photo? No, absolutely not. It's just that there are people behind the concepts that you learn, believe it or not. There are people, and some of these people actually, they're still alive. In fact, most of the people, you're lucky because you're in computer science, most of the people who did the stuff that you're studying every day are still out there. And many of them are actually still young, at heart or physically. So Noam Chomsky, amongst many of the things that he did, as a linguist, he was trying to come up with a formal explanation underlying the structure of the languages that we humans use. As it turned out, the type of formalism that he put forward which is the formalism of grammars that we just used, was not sufficiently powerful to deal with all the subtleties of natural language. But it turned out to be just the thing to use to describe the languages that we use to interact with computers. And in fact, he introduced this material long before you were born, 1956. So this is a classic. For some of you, this is prehistory. It's even prehistory for me. Now, Chomsky today in computer science is known, amongst other things, for what he called the Chomsky hierarchy of languages. And here's an egg-like description of this Chomsky hierarchy. Here's a description of the general formalism. Now, the type of grammar that I introduced before, I'm losing my voice now. Sorry, guys, you're at home. I'm regaining my voice right here, right now, so we are back online. Excellent. The type of grammar that I gave you before, in the general form, they go under the name of type 0 or phrase structure grammar. These grammars are full-blown programming languages. Any algorithm that you can write in any of your favorite programming languages, you can write equivalently using those grammars. You may not believe it, but that's what they are. They are programming languages, even though they don't look like it. You can take any C++ program that you write, you can compile it down to a phrase structure grammar that does exactly the same type of computation. The kind of grammars that we've been looking at so far are so-called context-free grammars, and these are really fundamental objects in computer science. They are grammars whose productions have the form left-hand side should be a single non-terminal, right-hand side can be any string of terminals and non-terminals. All of the grammars that we've written down today are context-free, apart from the one on the challenging example that I glossed over. Context-free grammars are at the heart of the specification of the syntax of programming languages. And I will tell you why in a second. There are some more special types of grammar, which are the so-called regular grammars. The regular grammars are a specialization of the context-free grammars in which you cannot write an arbitrary string on the right-hand side of a production. But what you write on the right-hand side is a very special form. It's either a single terminal, or it's a terminal followed by a single non-terminal, or it's the empty string. There are several versions of this type of grammars. It is in fact sufficient to allow the rewriting of a symbol of a non-terminal with the empty string when the non-terminal is the start variable. There are many different equivalent ways of describing regular grammars. You can also allow rewriting rules where a non-terminal can be replaced by the empty string or by a terminal followed by a non-terminal. These are all equivalent specifications. So for instance, the grammar that we wrote before for the language of strings of zeros followed by ones with the same length, that's not a regular grammar. Remember, we had a production that said S goes to 0, S1. That's not allowed. It's not allowed because you can only have one non-terminal, and it should be the last symbol that you write. It cannot be followed by anything. Okay? So why am I introducing this? For two reasons. First of all, if somebody asks you to prove that a language is context-free, all you need to come up with is a grammar which generates that language and is a context-free grammar. If somebody asks you to prove that a language is regular, all you need to do, or one of the things that you can do, is to write a regular grammar that generates that language. And what it takes for a language, for a grammar to be regular, well, the production that you use should have one of the allowed form. You're not allowed to use something which is not legal for that specific type of grammar. Let's put this in practice. Look at the first language. The first language says, give me all the strings of A's and B's which start with some number of A's followed by some number of B's. There doesn't need to be any relationship between the number of A's and the number of B's. That's why there is an N here. Give me N A's followed by M B's, where N and M could be arbitrary. My claim is that this language is regular. Can you come up with a regular grammar that generates this language? I'm sure you can. Let's do it. So here's the grammar. First of all, here's the language I want to generate. All the strings that start with a block of A's followed by a block of B's, but both N and M can be any number. Okay? I'm arguing that this language is regular. Let's first of all try to give a recursive specification of this language. What is the shortest string in this language?
A and B, 1B.
Okay, your colleague is saying A and B, 1A and 1B. Well, there's actually something shorter than that. It's the empty string. You can write 0 A's followed by 0 B's. So let me call this language L, because it's always a good name for a language.
But doesn't it say it has to be greater than 0?
Greater than or equal to 0.
Didn't see that.
So lambda is in L. That's a base case. So suppose Father Christmas gives you a string which is in L. How can you make it longer? Now, the string which is in L has this form. Some number of A's followed by some number of B's. If we did our recursion so far correctly, this string must have this form because this is what it takes for the string to be in there. How can we make it longer? What is it that you can do? You can put something in front. And what is it that you can put in front? We can put an A in front. However, does there have to be any A in front of a string? Not necessarily. Strings in this language can also contain only B's. So, okay, we could put a B at the back. We could put a B at the back. Just a second. Oh, the class should just be finishing now. Yes, the class is finishing now. The question is, or the statement was, the class should be finishing now, and I'm finishing now. So, question for you, turn this recursive specification of the language into a grammar. And then ask yourself, is this a regular grammar? And the class is officially finished now. Oh, by the way, in general, the class is finished when I say so. That's the only thing that makes me feel like